Okay, let's get started. So let's see, we're in the middle of this first exposition of the Fourier transform. And we started with just looking at the Fourier series, the idea that you can express some periodic signal of arbitrary shape with a set of sinusoids with the same period or submultiples, complete multiple cycles in that period. And then we showed that generalizes, if you let the period get very long, into the general Fourier transform, the continuous time Fourier transform, where you can take an arbitrary waveform without any explicit periodicity and express it in terms of sinusoids of arbitrary frequency, and where we can calculate the weight, the amount of the contribution of each sinusoid into the continuous time function by taking the inner product, the integral of the function we're trying to represent with the sinusoid, or actually with the conjugate complex sinusoid. Integrate that over the entire signal, and we get the coefficient that we have to scale that sinusoid by when we're trying to rebuild the signal by summing up sinusoids. That's the basic idea of the Fourier transform, and it's these two equivalent representations of a signal. We can either describe a signal as a continuous signal as a function of time, where it has some arbitrary, in general, complex value at every time instant, or we can describe it as a function of frequency, where it has some arbitrary complex magnitude or value and intensity for every possible frequency, complex conjugate or complex sinusoidal frequencies, both positive and negative frequencies. But the point is those signals, those two representations are symmetric, almost entirely symmetric, in that the forward Fourier transform looks a lot like the inverse Fourier transform. And they're both equally rich, equally useful, equally valid, at least from mathematical terms. From real terms, from practical terms, they're quite different. The time domain representation is the thing that we see, the sort of the literal real-time experience of the signal. The frequency domain representation is something completely different. Suddenly time is now, something that's implicit in every coefficient, and it's the frequency axis that's varying. But by the same token, that gives us a much more useful way to understand, or a useful new way to understand and manipulate signals, because now we can talk about that frequency content. We can manipulate the frequency content directly, and this is something that's kind of awkward and not obvious at all in the time domain. Okay, so that's the Fourier transform. Now we put it into the discrete time domain when we come up with a discrete time version of the Fourier transform, the DTFT. And basically, it's just what happens if you have this additional constraint that your signal is only defined at discrete time intervals, at discrete sampling intervals. And so now we have a relationship between a sampled sequence x of n and a spectrum, a Fourier transform, x of eta j omega. It's still a continuous valued spectrum, but now it becomes periodic in the frequency variable, in little omega. And that's the consequence of it being sampled in time. So it's still continuous value, but it now is periodic with period 2 pi. So we went through all that, and all the same stuff that we kind of expect works in discrete time with a few modifications. And we just finished by coming to this point that the DTFT, we'd seen that convolution was a very important and fundamental property of systems in general, in particular discrete time systems for our case. And then, so we're now looking at what the Fourier transform of the convolution of two signals is. So if we have two sequences, g of n and h of n, we convolve them to get x of n. What is the DTFT of x of n in terms of the DTFT of the individual sequences that were convolved? We can do that just by writing our DTFT expression around the convolution here, and then replacing the convolution with the convolution sum, and then doing the thing that it seems like you always do in these situations where you interchange the two summations and rearrange. And what we get is we can break up the e to the j omega into terms that match the arguments of these two summations. Right? This e to the j omega n becomes e to the j omega n minus k, and e to the minus j omega k, sorry, e to the minus j omega n. And so what we end up with is this, which with a change in the summation variable is simply the DTFT of h of n, and this, which is the DTFT of g of n. And so the DTFT of the convolution is the product of the DTFTs of the individual sequences. So it's a neat little piece of math, but it's a very, very profound observation, because now it means when we have systems with signals running through individual blocks, rather than having to express what comes out of those blocks as the convolution of the input with the impulse response of the block, we can simply write it as, if we express the whole thing in the frequency domain, we can write the output as the product of the spectrum of the input and the spectrum of the block. And that means that basically we can now use our familiar multiplication algebra to do manipulations and analyses of systems, of networks of blocks. So this is the DTFT pair. The DTFT of two signals convolved in the time domain is the product of their DTFTs in the frequency domain. So since that works, that we can calculate the spectrum of two signals by spectrum of the convolution of two signals by multiplying them together, that actually means that we could calculate the convolution of two signals by calculating their spectrums and then doing the inverse DTFT. Something like this, where we have two input signals. We want to calculate y of n here as the convolution of these two. We could just do the direct convolution sum, but for some reason, if we want to, we can do this instead. Take the DTFT of these two signals to give us g of eta j omega and h of eta j omega. Multiply those, so for every value of omega, we calculate the real value, the literal complex values of these two spectra. Multiply them together point for point, get a new function of omega, y of eta j omega, then we do the inverse DTFT to get y of n coming out. This sort of looks the same, as if we had some kind of convolution operator in here. But remember, the thing we said about convolution was it's not like multiplication, because you can't just take g of n for some value of n and h of n for some value of n and calculate that convolution for that value of n. You need to know entire sequences to calculate convolution, so it's not something you can calculate step by step under usual circumstances. And that's sort of implicit here, because to calculate the DTFT of g of n, we have to know the whole of g of n, right? It's the sum of g of n e to the minus j omega n for all n. So this sort of looks like a nice block diagram that maybe we could build on a circuit. But in fact, that's kind of hiding what's really going on. That we can't get this output until we've seen all of this. We can't get this output until we've seen all of this. We can't generate this final output until we've calculated all of this. And so this is not a real-time flow diagram. It's more of a notional thing that if you had finite length sequences, you could then and you knew them all, you calculate these, and then you could calculate the output. Of course, we can't even calculate the DTFT really, because it requires this infinite sum. But what we can do is we can do algebra with it, right? We can manipulate it on paper. And so here's an example of using what we know about the DTFT to do some closed form manipulations. So if we're saying x of n is alpha to the n mu of n, so it's an exponential sequence, right-sided, it's 0 for n less than 0. This is one of our identities. This is x of eta j omega is 1 over 1 minus alpha eta j omega. It's the one we looked at the beginning that has the kind of periodic bump, or the sort of the reciprocal of this spiral out around 1, 0. Okay, so that's alpha, x of n. H of n is now, we're going to define as delta of n minus alpha delta of n minus 1. So the impulse response here is very simple. Has a 1 at 0, has a minus alpha at 1, and it's 0 everywhere else. We can use our DTFT identities to calculate the DTFT of this. The DTFT of delta is 1. DTFT of delta n minus 1 is 1 times e to the minus j omega 1, a delay by 1 transformation, and then we scale it by alpha. So it's just 1 minus alpha e to the minus j omega. And so if y is the convolution of these two, then its DTFT is the product of these two DTFTs, which is just 1 over 1 minus alpha e to the minus j omega times 1 minus alpha e to the j omega. Here, the numerator is the same as the denominator, so they cancel out. So we get the DTFT of y of e to the j omega is equal to 1, which means that the y of n is just the I DTFT of this. We know that the thing that gives us the DTFT of 1 is delta. So y of n equals delta, which means that the convolution of x and h here is an impulse. What does that mean? I think I heard someone say it's an inverse system. That's right. That if X was the impulse response of some particular system we're putting through, which is, not an unreasonable impulse response, if we then put that output through an H, we'd undo the effect of X because the net result of putting it through both these systems would be a delta, which is the identity of convolution. And so that these form an inverse system pair. And so that's something that here, this is basically you take alpha of the output and feed it back. And here, you take the current input and the previous input, and you subtract alpha of the previous input, and that's basically undoing this sort of feedback loop that's implicit in that impulse response. Okay. Now, what about if we multiply two signals together in the time domain rather than convolving them? So if we had x of n is equal to g of n times h of n, how can we get the Fourier transform of that? Well, if g of n was just a sinusoid, we'd sort of know what was going on there. That would be modulation, and hopefully we have this intuition that when you multiply by something by a sinusoid, you're modulating onto a carrier. You shift the whole spectrum. We had an identity that the DTFT of e to the j omega 0 n times x of n is x of e to the j omega minus omega 0. It's a shift in omega. Well, g of n in general won't just be sinusoids, but we know how to express it as the sum of sinusoids, and then because of linearity, we can say, well, if we express g of n as a sum of individual sinusoids, then the DTFT we're looking for is just the sum of the individual DTFTs with those sinusoids. So expressing g of n as a sum of sinusoids is just expressing it with its IDTFT here, right? So we're saying g of n is equal to the integral of g of e to the j omega, but we're using theta here just to avoid confusion. E to the j theta times g of e to the j theta times e of e to the j theta n d theta, right? That's just the IDTFT, or the synthesis integral. There's 1 over 2 pi scaling here. So that's just this in here. And then we're taking the DTFT, so here's our sum over e to the minus j omega n, and multiplying by h of n, which is what we're doing up here. And so now, once again, we can do this thing of interchanging the order of these two summations, or summation and the integral. And I don't know, I mean, heuristically, that's kind of it's the number one trick to try in these kinds of proofs. I mean, you'll never have to do this, but it's just worth, it's like, well, how do they do this? It's like, well, it's always worth playing with. And in particular, what we're trying to do is we're trying to separate out if we can separate out the n, then we can start doing interesting things, right? So here we're trying to gather all the terms in n in here, and that helps us out. We can do that when we change this around. What we end up with is this, which looks like the DTFT of h, but it's the DTFT of h as a function of omega minus theta. And then we've got the DTFT of g out here. We put that in to begin with. And so we end up with this thing, which is now, so this is the Fourier transform pair. The Fourier transform DTFT of h of n times g of n times h of n in the time domain is this, which is actually this is a convolution in the frequency domain. It's an integral of one function of theta times a different function of omega minus theta. It's a function of omega here, implicitly. And so this is, you recognize this over all values of theta. So it's just like a regular convolution. We've got an integral with a dummy variable. We've got one function of the variable multiplied by the other function of something minus the variable, time flipped and shifted, to give us a function of something. That's the convolution. It looks kind of weird because of the e to the j argument. But that's what's going on. And of course, that's satisfying because when we convolved in time, we got the product in the frequency domain. Now when we form a product in time, we get a convolution in the frequency domain. So again, it's this duality between time and frequency. And what's the difference? There's this There's this 1 and 2 pi scaling, which is always sort of in the loop somewhere. Otherwise, I think it's pretty much the same. Okay, see how that works out? See what that means? So again, this is saying that there's precious little differentiation between the time domain representation and the frequency domain representation. They basically do, they behave very similar in respect to one another. Some other things. Parseval's relation is this interesting property of transforms, of energy-preserving transforms. And what it says is, well, the intuition here is, if you have some signal somewhere in one of your domains, when you transform it into the other domain, the signal gets spread out and moved around. That's the whole point of doing the transform. But the total energy is maintained. That sort of, makes sense from the point of view of linearity, that if you have a zero energy in one domain, then the Fourier transform has got to be zero. If you get it larger, it's got to be larger somewhere. But it's not necessarily obvious that it's going to be precisely the same energy. By the special properties of the particular basis that we're using, it works out. And we can generalize it slightly. So this is the generalized form, that if you have two sequences and you multiply one by the conjugate, the complex conjugate of the other, and then you sum over all time, then the sum of those two time domain functions over all time is equal to the sum of the product of their frequency domain functions, g and h conjugate, over all frequency. If g is equal to h, then g times h star is the magnitude of g squared. Big G times big G star is the magnitude of g of e to the j omega squared. So the whole thing then just becomes energy. And that's normally the way we think about it. That's kind of what I described as the energy being equal in two domains. But actually, you can use it for any inner product between two signals. And of course, the fact that we're writing one of them as a conjugate is arbitrary if we could define another signal that way. But that makes the relationship look nice and simple like that. So just to sort of follow that through, we can define the energy of a sequence as the sum over all time of its squared values. Hopefully if it's finite length, this will be a finite value. And we just saw that by the Parseval's relation, that's the same as the integral of its magnitude squared of its spectrum over all frequencies, right? And this is, because this is periodic spectrum, all frequencies is just from minus pi to pi, because beyond that it just repeats. And so if we've got something which says, well, if you add up this quantity, the magnitude squared of the DTFT, if you integrate it over all frequencies, you get the total energy of the spectrum. It then makes sense to think about, so the individual values, the g of e to the j omega magnitude squared for some value of omega is some part of the energy. It's like, okay, it's not invalid or dangerous to think about individual pieces of the spectrum having energy, because it sums up to energy. It may be a strange concept because we're used to thinking of energy as something you can chop out in time, and in the Fourier transform, it's energy that's spread across all time. But at least it makes sense, at least in terms of the integral. So we can talk about the magnitude squared of the DTFT as an energy density spectrum, just like this. This is really just a definition, right? There's nothing being said in here. It's just we're giving a name to magnitude of g of e to the j omega squared as SGG of e to the j omega. But we're calling it, the name we're giving it is energy density spectrum, because we're saying it's how much energy there is at different frequencies. And of course, it's real and non-negative because it's a magnitude squared. It can't be complex and it can't go below zero. Now, autocorrelation, we defined RGG of lag L as this sum over all time of g of n times g of n minus L. It was like convolution, but with the sense of the second sequence reversed. This is autocorrelation, so it's g and g here. And we noted that it's the same as convolution with the time-reversed version. So it's g of n convolved with g of minus n will give us the autocorrelation. If we think about applying our DTFT identities to this, the DTFT of this sequence is going to be the DTFT of this. The convolution of the DTFT of the convolution of two signals is the product of the DTFTs of the individual things. And then the DTFT of the time-reversed version of a signal is the conjugate. Oh, man. Oh, here we go. Yeah. So the time-reversed signal is the reversing in frequency. But if we have a real signal to begin with, then the spectrum itself will be conjugate symmetric. So when we flip it in time, we get the conjugate of that, conjugate of the signal coming out. And so then this becomes g of e to the j omega times g conjugate of e to the j omega. So we get the autocorrelation as the Fourier transform of the autocorrelation is this thing we just defined, the energy density spectrum. And so that's kind of a nice little twist that autocorrelation followed by DTFT is the same as DTFT followed by magnitude squared, because autocorrelation is multiplying, autocorrelation of a real sequence is multiplying by the time-reversed version, which is whose Fourier transform is the conjugate spectrum. And what this is saying is that if I give you the autocorrelation, you can look at its spectrum, and you can know where all the energy was, at what frequencies the energy occurred in the original signal. Not in autocorrelation, but in the original signal, right? So it's telling us something about G from RGG. But all it's telling us is the magnitude squared of the spectrum. It doesn't tell us anything about the phase of the individual components, because that's the thing you lose when you take the magnitude squared. And what that means is the same as saying we've sort of lost information about where in time this energy occurred. Now, in the spectrum, there isn't any where in time, but in the shape of the, obviously, if we take a Fourier transform, we preserve the entire signal. We can take the inverse Fourier transform, we get the time structure back. But in some sense, that time structure is being encoded in the relative phase of different spectral components. But when we take the autocorrelation, we sort of lose the time information as well, because if signals like this, if a signal has structure around 0, has particular autocorrelation, but if it has structure at some other time, the autocorrelation can be the same. Autocorrelation is invariant to a shift in the underlying signal, because you're just looking at signal relative to shifts of itself. And so both the autocorrelation and the energy density spectrum are descriptions of the signal that have taken away the information about where it is in time, or the structure in time in some sense. We'll probably come back to that. That's just a little thing to notice and to think about as we go on. All right, so that's kind of the introduction to the discrete-time Fourier transform, which is this continuous function of a discrete sequence. But as I mentioned, it's something that isn't actually that useful to us, because if we're working on computers, we don't particularly have a good way of representing a continuous function on a computer. The best way to do it might be as in terms of a set of continuous basis functions, which would be just to represent it as the time domain representation. But we really want to be able to actually have and manipulate frequency domain representations, which means that we need a representation which is discrete in frequency as well. And here's a good candidate. The discrete Fourier transform, not the discrete-time Fourier transform, but the fully discrete Fourier transform, was the fourth row in that table we had of the 4 different kinds of Fourier transforms. And it operates on a discrete sequence x of n, but the x of n is also finite dimensional. It's defined by just some fixed number of values, which we can either interpret as it being finite length, so it's only defined over a fixed number of values, or it's periodic, so you can evaluate it for any time, but it repeats every big N sample, something like that. When that's the case, then we can represent its spectrum also by a finite dimensional sequence, x of k, where k is now our index for the frequency domain. And now we're back, just as the full-up continuous time Fourier transform was a mapping between a continuous function and a continuous function. We now also have a symmetric pair here, a mapping between a discrete finite length sequence and a discrete finite length sequence, which of course is also going to make it useful for our computers, which can only deal with discrete finite length sequences or vectors. So a finite or periodic sequence has only big N unique values, which we can say define as x of n for 0 less than n less than or equal to n less than big N. And so if we, there are only n degrees of freedom for the time domain sequence, we can calculate the spectrum, right, either by viewing it as a sequence that's 0 outside the range or by viewing it as a periodic sequence. We can calculate its DTFT, but it seems like the DTFT we really ought to be able to describe with just big N values, because there really are only big N things that can vary here, and it's a one-to-one mapping. So there are various things we could try and imagine working here. But one thing we could say is, well, I've got this sequence which has a DTFT, which is continuous, exists for all frequencies. And if I just take big N samples of that, then if I'm lucky, those will be the big N constraints, the big N degrees of freedom that will give me the whole spectrum. And maybe I can just take the 2 pi unique chunk of the spectrum, right? The spectrum is periodic in 2 pi x v to j omega. If I divide that into n equal steps, that is, I uniformly sample it in frequency, then that's one way of getting big N values out here. So I could evaluate the DTFT at a set of big N frequencies, omega sub k, which is just 2 pi k divided by n. That is the 2 pi on n times k, 1/n of the entire sequence. And that would give me what I want. And that turns out to be what we need. It gives us the discrete Fourier transform. So we're going to say that x of k, the DFT, is x of e to the j omega, the DTFT, for a set of discrete values of omega, where omega is equal to 2 pi k on big N. If we plug this back into our DTFT equation, right, DTFT is sum of x of n e to the minus j omega n, so now we've got omega is equal to 2 pi k on n, so it's x of n e to the minus j 2 pi k on n, on big N times n. The DTFT is the sum over all possible values of n, but here we're saying that x of n is over a finite range, so let's assume it's 0 outside that range. So now we can just restrict our summation to just n equals 0 through big N minus 1. And that gives us x of k, a frequency value for an index, where this index, we remember, is just sort of uniformly sampling the omega space, little omega space. This is a little clumsy because, got a lot of numbers in there. So we can actually, just to make the notation a little simpler, we can define big W sub n as this number here, right, this part. Slightly strange thing to define it as, but if we define it that way, then x of k is just the sum, n equals 0 to big N minus 1, x of n times W sub n to the kn. That's kind of neat, so we can see that we've got this single basis. We multiply it, we raise it to the power of the time index and the frequency index. We take the inner product against those, and that gives us the individual frequency bin. That's just, rearranging the DTFT equation subject to these two conventions. So this thing, W sub n, what it is, it's e to the minus j 2 pi on big N. So e to the minus j something, e to the minus j omega is a unit vector with angle omega, or minus omega in this case. And so the angle here is 2 pi on n, which is 1/n of 2 pi, 1/n of a whole revolution. So it's a little vector like this, which is just, half going negative-wise in phase, how far you'd have to go, such that if you did it n times, you get all the way around. That's just what the math gives us. So that's the DFT. If we want it to be a well-behaved Fourier transform, we want to make sure that we can also inverse it or have a synthesis equation. Here's the IDFT, which again is the same kind of thing, but we're going to take the spectral values, multiply them by complex sinusoids, and sum up overall frequency values. There's a 1 over n scaling in here, and then we can express this complex sinusoid as our W sub n. W sub n was e to the minus 2 pi on n, e to the minus j 2 pi on n, so now we have to raise it to a negative power to get a positive going complex sinusoid, but it's basically the same thing. And we can verify that this works, like we do before, by substituting in the DFT here into the IDFT equation. And we can then rearrange it, so we get the sum over x of L times the sum over this dummy variable k of W sub n k to the L minus n. And what we want this to do is we want this thing to go to 0 if L is not equal to n, and to equal something non-zero when L equals to n. Actually, we want it to equal to n because we've got this 1 over n scaling constant we're trying to get rid of. This works. The way I think about this that sort of appeals to me is, well, each of these W sub n's is one of these little vectors, right? The unit length vectors with an angle which is 1/nth revolution rotated by whatever the exponent is here. So if you have W sub n to the k times 1, right, then, and we're summing it from k equals 0 to n minus 1, well, this would be W sub n to the 0 times 1, which is, if you raise it to the 0th power, you get 1. Here it is W sub n to the 1th power, just itself. W sub n squared is the same thing, but then rotated twice, so it's 2nths of a revolution. And you sum them all up, and it turns out that if you think about what's going on, when you sum them all up, they sort of loop out. Summing up is just sticking them end to end, right? Sticking the vectors end to end. They loop out, but they actually come back to the origin. So the sum of this for exactly n terms for a non-zero exponent here always gets you back to 0. And if this is for 1, if it was 2, then it would actually be, it would sort of do it twice as fast because the angle each time would be double the angle. So it would actually do 2 complete loops, but it would still end up at 0. But by thinking about it that way, you can see that this thing always sums to 0 unless L minus n is 0, in which case, they all just stack up end on end. And so you get n times 1, which gives you the n you need to get rid of this 1 over n over here. I like that geometric interpretation. You can also prove it algebraically very quickly by using a finite geometric sequence, finite geometric series. Remember that we've had if s equals sum of alpha to the n, then we multiply alpha by s and subtract them out. When you have a finite sequence like this, then you end up with a term sticking out the end. But when you work this through, you'll see that it also works to give you the correct answer, which is that these terms all disappear except when L is equal to n, so x of n does indeed give x of n. The IDFT plugged into the DFT equation, the DFT plugged into the IDFT equation gives you identity. Okay, so here are some examples of calculating DFTs. So remember, when we do this, we often start off with the impulse. That is, x of n is equal to 1 for n equals 0, and 0 otherwise. But here, we're talking about a domain where x of n is finite length. So it's either an impulse with a finite extent, or it's a periodic impulse. I'm raising both of these possibilities because, in a sense, the same math represents both of them, right? We're dealing with this time domain, which is now only big N points long. And we can either read that as a finite length sequence that's 0 for the rest of time, or as a periodic sequence. And it turns out from the Fourier transform domain, there's a different sequence, right? In real time, in real life, the difference between a short sequence and a periodic sequence, they're completely different. But from the DFT domain, they're the same, because it turns out that in these big N frequency samples, we'd represent them the same. So that's why I'm sort of being ambiguous about which one it is, because it doesn't actually matter in terms of the math. But if we think about this as a periodic sequence, this is now a periodic impulse. It's a 1 every big N samples. But that's the best impulse we can have in finite dimensional sequences. Okay, so the DFT is the sum of x of n, w, that should be a big N there, sorry about that, w sub n to the kn, which means that it's x of n is only non-zero for n equals 0, so it's w big N to the 0, which is 1. And so it works out that just as in the DTFT domain, the DTFT of an impulse was 1 for all frequencies, here the DFT of an impulse is 1 for all frequencies, which is only n different frequencies. But yeah.
Can you just explain one more time why it doesn't matter if it's periodic or not?
Okay, why does it not? Why am I sort of waving my hands about this difference between periodic or finite length? I could just say I'm talking about I could just choose one of them, right, and just say, okay, now we want to have this finite dimensional signal that we're talking about. So here's how we can define it. We can just say either we're talking about a finite length sequence so that everything by definition is 0 outside of n equals 0 to n minus 1, or even more kind of abstractly, there is no time axis outside that range. Or we could say we're talking about a continuous time sequence that an infinite duration discrete sequence, which is periodic with period n. But there are occasions for where both of those would be useful. And so rather than having to deal with them separately, I'm trying to deal with them both at once, because it turns out that mathematically they're equivalent. We have that has a slightly different impact, right? So the DTFT is x of e to j omega is equal to the sum for n equal all possible values x of n e to the minus j omega n, right? And so if n is defined as 0 outside of some range, then it naturally becomes the sum from n equals 0 to n minus 1 of x of n e whatever, e to the minus j omega n, where we can define omega differently. So that's like the DFT is exactly the DTFT for a finite length sequence of n points. If x of n was periodic, then this would not be true anymore, because then it would be like this, and then another one for the next n, etc., etc. But then if x of n is periodic, x of n is infinite energy, because its energy never goes away. And so then it's like it doesn't have a Fourier transform you can talk about. But we could say, well, if we restrict this to being the sort of, the per period average, then it all works out again. And so, the Fourier if you did have a truly periodic sequence, which means that it goes on forever and it has infinite energy, its Fourier transform would be infinite, right? How much energy does it have at its fundamental? Well, if you sum up the energy over all time, it has an infinite amount of energy. But we can still talk about it, because we can say, well, imagine that we were averaging it by how long we looked at it. That converges, and that converges to this thing. So it's a little more clumsy to think about, and I recognize I'm not being at all rigorous there. So maybe we should think mainly about the finite length version, where it's just this is a sequence that's 0 outside some range. But we know in the backs of our minds that this stuff also works if we have a periodic sequence and we imagine just analyzing one period of it. Okay. All right, so that's the impulse response. The DFT of an impulse, which is in this case a finite length impulse, gives us the same answer. You see, it's not very, in the finite range, that's not very interesting, right? It's like, well, yeah, it's the same answer. Whereas it's sort of more interesting when you talk about this as a periodic impulse, because it's also true there. What happens there, the periodic impulse doesn't have a flat spectrum. It has some spectrum with lots of harmonics in it. But when we take x of k, we're always sampling on the peaks of the harmonics, so we only ever see the flat part. We'll see more of that in a second. All right, if we have a x of n, which is a sinusoid, because x of n is periodic, it better be a sinusoid that completes an exact number of cycles in big N samples. So that's why I'm saying a periodic sinusoid as opposed to one of those sinusoids. It doesn't quite land up at 0, so it's sinusoidal, but it's not a periodic sequence. So this is our periodic sinusoid. We can express this in terms of our big W, right? Because big W is the sort of the basis that forms exactly one cycle in big N samples. So if we have something that's completing R cycles in big N samples, it's just W sub n to the Rn. And then if it's an exponential sinusoid, it's just that. If it's a real sinusoid, we have to make it by combining two of these to cancel the imaginary parts. This is the positive frequency one, the negative frequency one. The cosine parts are the same. The sine parts, which are the imaginary parts, are conjugate, so cancel out. So we take the average of those two, we get a cosine. And then if we plug this into our DFT equation, right, it's all, oh man, it's that little n again. This should be a big N. I just redid these this morning because I was trying to make the fonts look nicer. And so anyway, this is the same basis, exponential basis, so we can add them together. And so basically we end up with a sum of W sub n to the k minus Rn and W sub n to the k plus Rn. And by that argument, by about sums of W sub n to the kn, making loops, unless the exponent is 0, that's only it's going to be 0 unless k equals r or k equals minus r, in which case it's going to be n and then n over 2. But k is not going to be equal to minus r because k is restricted to be between 0 and n. However, it can be n minus r, which is sort of minus r shifted over by one period of n. And then this also works out to be the same because w sub big N to the n minus r is w sub big N to the n times w sub big N to the minus r. W sub big N to the n is just 1, so it disappears. So again, with these periodic things, you sort of have to be a little bit careful about which range of indexes or values you're talking about. And so that is saying that for this sinusoid at completing r cycles per big N point window, the spectrum is 0 for all frequencies except for the indices that correspond to the positive version of that frequency and the negative version of that frequency aliased onto this big N cycle. So big N, k equal big N is the value that doesn't occur, but it's like we get back to 0 again because it's of the periodicity and frequency. So this would be k equal to minus r if we had a minus r in our range. That is not something you have to memorize. It's something that once you think about what x of k is actually representing, x of k, here's another reason to introduce the idea of periodicity. X of k is definitely a periodic sequence in frequency, right? Because we know that the spectrum is periodic in period 2 pi. So now, once you think about that, we're representing x of k by its values between 0 and big N minus 1, but we're understanding that it repeats for all other values of k.
Do you mind just drawing on the board real quick?
Yeah. What?
Yeah, so this representation.
Oh, what this signal looks like? So, I'm just saying, okay, so this is k, which is our discrete frequency index. And so now k actually goes between 0 and n, or it doesn't actually quite reach n, but it has a set of values here up to n minus 1, right? Sorry. And what we're saying is that this sinusoid that completed r cycles has a value here. All these values are 0 except for this one at r. And so this is r here, and this is r here. There's another non-zero value here at n minus r. And in both those cases, it's actually n on 2 for a unit amplitude cosine the k's. And so, but this is now we can use our stem representation because now x of k is a discrete sequence like that. Because it's cosine phase, both of these values are real and positive. In general, they would be complex values. But in this case, they happen to both be complex values whose imaginary parts are 0. Okay. Because of this, fact that we're dealing with finite length vectors, finite length sequences, we're now squarely in the domain of linear algebra. Here's our DFT expression. It's just a set of inner products, if you like, between the finite length sequence and certain other finite length sequences. So we can write the whole thing down as a matrix multiply, where this is now a finite, this is now a nice n by n, big N by big N matrix. So we can call that D sub n. We can say that the vector of the DFT values, which I'm writing as big bold X here, just big X 0 through big X n minus 1, is just dn times little bold x, which is my time domain vector representation, little x 0 through little x n minus 1. And then each row is like, this is just w sub big N to the kn for different values of k, right? This is the value for k equals 0, k equal 1, k equal 2, so it's w sub n to the 2 times 0, w sub n to the 2 times 1. So this is, here each row is a value of k and each column is a value of n. And those are the w to the kn's for those values. So that's nice. Matrix multiplication is something that computers are good at. Often you have optimized libraries for this kind of thing, so that gives us a nice way to think about it. And then we can also use our insights from linear algebra to understand what's going on. So if this is now our expression of our DFT, frequency domain is this matrix times the time domain, then we can write the IDFT as the inverse of that, right? It's just getting back little x from big X. So little x, and we know how to do that in matrix land. We just have the inverse matrix. Little x is d sub n to the minus 1, meaning matrix inverse, times big X. And we've actually already written down the IDFT equation. And so it's just the 1 over n w sub n to the minus nk. And so that's these parameters here. But of course, if we actually calculated the matrix inverse of the n by n matrix that we had before, d sub n, we get this value too. And however you want to do it. This is like the determinant, and then there's some thing you do to invert different values. We also notice that this inverse, this IDFT matrix, looks a lot like the DFT matrix, except for the 1 over n and the exponents of the individual terms here. So negating the exponents of these terms, remember this term is just a unit complex vector, unit length complex vector. So raising it to a negative power is the same as conjugating it. And so d sub n to the minus 1 is just 1 over n times d sub n conjugate. That is to say, the DFT and the IDFT are basically the same matrix multiplication, except you conjugate the matrix, and then you have to scale by 1 on n in one sense, which is like the 1 on 2 pi that you have in the loop when you do a Fourier transform, inverse Fourier transform. So this is neat, and this means, while we're just in passing, that if we have an algorithm, if we have a piece of code that calculates the DFT, we can make it calculate the IDFT pretty simply by exploiting this. So now we've got something which is a Fourier transform which we can use on actual signals, on explicit signals, that we can calculate on a computer, for instance, by using MATLAB. Whereas the DTFT, which was a continuous function of an unlimited, indefinite length sequence, is not something we can directly manipulate on a computer. What we can do, of course, is we can calculate the DFT expression, the DTFT expression, the sum of x of n e to the minus j omega n, for any particular value of omega. And then if we calculate it for the values of omega that are 2 pi k on n, then we get the DFT coming out. So 2 ways we can do this in MATLAB. FrexZ does just that. It calculates the inner product between a sequence and a sinusoid of a particular frequency omega, or a set of frequencies for a vector omega, which is sort of sampling the DTFT at particular frequencies. The one here we'll talk about later. But you can just if you leave it as 1, then you just get the samples of the DTFT, which is the DFT. And then for the direct form, we have FFT, which is the fast Fourier transform, which is a fast algorithm for calculating the DFT. And so this just takes an endpoint sequence out, gives you an endpoint sequence, takes an endpoint sequence in, gives you an endpoint sequence out, which is just the Fourier transform of that sequence. I'll show you that in a second. Let's just get on to a couple more properties before we look at that. So let's just contrast and sort of try and cement the relationship between the DTFT and the DFT. So here I've written down the analysis equations, the Fourier transforms for both of them. DTFT, x of e to the j omega, continuous function, continuous omega, is the sum over all infinite time of x of n e to the minus j omega n. DFT, x of k, sequence, discrete sequence, finite dimensional, is the sum over a finite number of points of x of n, because that's all that we have. X, for n equals 0 to big N minus 1, x of n times w sub n to the kn, where w sub n is basically this for a particular frequency. But we can see that because it's the same x of n in here, and basically these things are the same function, just written in different ways. We have this relationship here that x of k is just x of e to the j omega for particular values of omega here. At least if x of n is finite length, then we can still calculate this, right? If x of n is longer than n points, then we won't be calculating it all in here. But if we have an x of n that really is only non-zero, only between little n equals 0 to big N minus 1, then we can calculate either of these, and they're related like this. And what we're saying here is that x of omega is some smooth, continuous function of omega. It's periodic in omega, but if we just look at, between 0 and pi, say, we get some smooth function like this. Then x of k is simply the value of that function at these uniformly spaced samples in frequency, right? 1/n of the entire unique sequence. And so that's why we can have this FrexZ function in MATLAB, which you can interpret either as evaluating x of e to the j omega at particular frequencies or as calculating the DFT. They're the same thing. So if you give me the DTFT and I want to find the DFT, then all I really have to do is evaluate at these particular frequencies. I could also think about doing it the other way around. I give you the DFT of a sequence, some finite length description of its spectral values at a bunch of frequencies, and then I say, what was the DTFT? What was that smooth, continuous function of frequency? I've got to be able to do it, because one way I could do it is I could take my DFT, I could inverse the DFT back to the time domain, then I could just apply the DTFT, right? So the information is there. The DFT completely specifies the big N unique points of the time domain signal, and the DTFT is maybe a continuous function, but it's based on these same time domain values. But maybe I can do it in one step, or just maybe I can algebraically combine those two steps. So that's what I'm doing here. Here I'm trying to calculate the DTFT, function of continuous omega, as the sum of x of n times e to the minus j omega n. But here, for x of n, I'm substituting in my IDFT, because I'm saying that if I'm starting from the DFT values here, x of k, then I can reconstruct the time domain values here. We have to be a little bit careful with our indices here, right? That the DTFT would normally be over all time, but here we're saying, well, this IDFT is only going to give me the n values between 0 and n minus 1, so I'll just do the summation over that range. And then we do the usual kinds of things of trying to reorder the summations to separate out the parts that might be usefully separated out. In this case, we can combine the e to the minus j omega n and the w sub n to the minus kn by rewriting it as an exponential form. And we can pull out all the x values here outside of this summation. We can change the order summation. We end up with x over the j omega equal to the sum of all the xk values, each one multiplied by something here. Now this looks like one of our things that normally collapses, an e to the j of something multiplied by n. But now it turns out that the things that allowed it to collapse in the past, which were that this was an integer times 2 pi, it's not holding here. We've actually got a continuous value omega in here, which is giving us a continuous value. We're going to evaluate this for any arbitrary, value of omega, so it's not going to collapse down. And also it's, well, yes. So what we end up with is this. It turns out that we'll see on the next slide that actually this part turns into this, and this thing looks it looks a little bit like our sinc function. It looks a little bit like sine x on x, but actually now it's what we call a periodic sinc because it's sine nx on sine x. So it's periodic in x, right? Because both the nx and the sine nx and sine x are both periodic in 2 pi of x. But there's something sinky going on here because it's sine of n times something divided by something else. So that's what we're setting up for here. And this actually, you can also view this as interpolation. That what we're trying to do is find these in-between values of omega between the values of k where it's sampled. So we're trying to interpolate a function, basically. So we'll see how that works out. So this part here, the sum of e to the j omega minus 2 pi kn, if we define that thing as delta of omega k, which is the difference between the kth DFT sample and actual omega, then that's what we need here. And it makes this a little bit simpler. So now, if we define it like this, as this is what we're trying to work out, we can use this finite geometric sum thing to say, well, if we multiply this up and then subtracted it by 1, right, if we multiply this entire sum by e to the j delta omega k, and then subtract it out, we get the end term sticking out. The first term is here minus the last extra term. All the other terms cancel out. And then if we divide through by what we scaled it by, we get this on the denominator. I'm sorry, I didn't explain that at all well, but it's the finite geometric sum identity. And if you're wondering where that comes from, you can just look it up, figure it out. It's just the sum n equals 0 to big N minus 1 of alpha to the n, right? It looks like this. Well, now we have this interesting thing. We have 1 minus e to the j n delta omega k divided by 1 minus e to the j delta omega k. And we can work on this in this clever way. We split out, as it were, the geometric mean of these two, the square root of this, which is e to the minus j n delta omega k on 2. When we divide that out of the 1, we get the reciprocal of this, which is e to the plus j n delta omega k on 2. When we divide out of this, we get the other half. This is basically the square root of this. So we just get the same thing again, this term again, right? So this, you can see this multiplied by this gives you 1. This multiplied by this gives you this. And what this is half of this angle, this phase here. This is just a complex phasor, unit length, angle, n delta omega k, and this is like half of that. We can do the same thing on the denominator, but now rather than splitting n delta omega k in 2, we're splitting just delta omega k on 2. We end up with this term, which is just the the ratio of 2 exponentials, so we can just combine them here, so we get j n minus 1 delta omega k on 2. And then we get these two terms, which are the differences of two conjugate exponentials. So they're just j sine. This is like cos n delta omega k on 2 plus j sine n delta omega k on 2. And this is cos n delta omega k on 2 minus j sine n delta omega k on 2. So we get 2j sine n delta omega k on 2. And then same down here, where now we get 2j sine delta omega k on 2. The 2j's cancel out. So we just get this thing just becomes this ratio of sines, this periodic sinc. And this part is a pure phase term, which just depends on delta omega k. And this is our interpolation weight. Rather than looking at the properties here, let's look at, whenever I touch this, it controls the other computer, which is why I'm grimacing. But it doesn't work. Okay, here's what's actually going on. Okay, here's our periodic sinc, sine nx on sine x. Here, green is sine nx, blue is sine x, and sort of close to 0, it behaves like sinc. Right? We have a sine function divided by something which looks kind of like y equals x, at least you don't look too far away. So you have this sort of sinc behavior where it looks like a sine that decays away, except at 0 where it tends to 1. Or in this case, it actually tends to n, because sine nx tends to nx as x goes to 0, and sine x tends to 1 as x goes to 0. Sine x tends to x as x goes to 0. But then the whole thing is going to be periodic. So if we go over here to 2 pi, it's got to be the same again, because both sine nx and sine x are periodic in 2 pi. And then what happens in between is this it has these ripples. It actually has, in this case, for an odd value of n, I think, it has these negative little ripply peaks here at n. But the whole thing is periodic in x with period 2 pi, but has around, locally has this sort of sinc-like behavior where it's trying to do n ripples and then sort of has to build up again. So that's why I call it a periodic sinc. Now what happened, right, if we go back 2 slides here, we were trying to reconstruct x of e to the j omega from x of k, and it turns out that for any given value of x of e to the j omega, we take all the values of x of k and then multiply them by this term here with this phase correction term in here. What are the values in there that we're multiplying them by? Well, so that's what I'm trying to draw here. Here, the individual lines are particular values of x of k. X of k is x of e to the j 2 pi k on n, right? They're values of the DTFT for some particular value of omega k. The colored lines here are the periodic sinc interpolation functions, which are the amounts that this particular x of k gets multiplied by when I'm trying to calculate x of e to the j omega for some value of omega. And then the black line is simply the actual e to the j omega function, which is the sum of these x of k's times their periodic sinc functions when the phases work out. This assumes that the phase term, this phase term works out to be 0 for everything, which you can do if the x of k's are all real. But just allows you to see how what's happening is this red x of k value is contributing this kind of function to all values of omega, and then each of the other ones is contributing a function. You sum them up, and when you sum them up, you get this black line, which is the actual x of e to the j omega, the actual DTFT. And you can see that now it's interpolating between these points. Of course, when for omega equal to 2 pi k on n, that is when we're sampling, we're trying to reconstruct e to the j omega for one of the sample points, it just falls exactly on the sample. And that's because all these other interpolation bases all go through 0 at this point. The only one that's non-zero is the one that's corresponding to that particular point. That's classic behavior of an interpolating kernel. If you haven't come across those ideas of interpolation, that's not so interesting. But if you thought about that before, then it's nice to see how this fits in. I guess the bottom line is, yes, the math does work out. Of course, we can work out the intermediate values of x of e to the j omega from the DFT just by working the math. Yeah.
Can you go to slide 42, please?
Yeah.
So the final sum of a to the n isn't that usually 1 over 1 minus a to the n?
That is the infinite sum,
Oh, okay.
right? That was quickly revise that. So the sum of alpha to the n for n equals 0 to infinity, assuming that alpha to the n disappears because alpha is smaller than 1, is 1 over 1 minus alpha. But for sum of, and that was because we multiplied the whole thing out, took them out, we got this left over, we divided through by this. Now let's work this through for this one. Sum equals n to n minus 1 of alpha to the n. If we call s equal to that, then alpha s is equal to the sum from n equal 1 to n of alpha to the n. So s minus alpha s is like all these terms cancel out except for this one and this one. So we get alpha to the 0, and then we're subtracting this one off, so we get minus alpha to the n, right? And so now we can just say, well, that's 1 minus alpha s is equal to this, so s is equal to 1 minus alpha to the n on 1 minus alpha. That was, and this is the part that changes because we only have a finite range in here. Okay, let me just I'm sorry to make this more complicated because I feel like that conceptually it's like, yeah, it's a little bit strange. What are we trying to do? We're trying to get the DTFT back from the DFT. You know, they're kind of the same thing, but there's still some math to be had in there. Here's another thing we can try and do. We can try and get the DFT from the DTFT. Well, that's easy. We just evaluate at particular points. But let's say I'm trying to take a DFT, which is a big n-point DFT, but my DTFT is of a sequence which has more than n points. It's like, well, you can't, that's not going to work. We can't just take, a sequence of more than n points, represent it by an n-point DFT, and then have it come back. Obviously, we're going to lose some information there because now we can only represent big N independent values. But we can still try and do it, right? So if we have x of e to the j omega for some longer sequence, we can just evaluate its values at these individual points to get our x of k. But then if we take the IDFT of that, we're going to get something which is only an n-point sequence. So what is the relationship of this n-point sequence, which we could call, say, x twiddle of n, to suggest that it's periodic? How is that related to the original sequence x of n, which has more than n points? And again, we can just do this by working through the math. So here's the process. We've got x of n, which has some arbitrary longer length. We take its DTFT to get x of e to the j omega. We sample that at big N points to get x of k, for k equals 0 through n minus 1. And then we IDFT that to get x twiddle of n, which is now also only unique between 0 and big N minus 1. We can plug in the equations here, right? So here is our IDFT equation, and here is our DTFT, which we're going to evaluate at particular values of e to the j omega, of little particular values of omega, which we can get by just using w in here. And then when we do this, we can again rearrange and interchange. And we find that we get x of n is equal to the sum over all L of x of L times this term in here, which we recognize as the one that is well behaved. It's the w sum of n, w sub n's raised to powers. This thing is going to be 1 when this exponent is 0, and 0 otherwise modulo big N. So it's going to be 1 when L minus n is 0, but if L minus n is n, or a multiple of big N, then it might as well be 0 because we can split it out to be this omega sub n to the k big N, which disappears, becomes 1. And so now we have this thing which is only 1 when L minus n equals 0 if L and n are both in the range 0 to n minus 1. But if and L is only, no, n is only in that range, right? N is the index of our periodic thing. But L can be any value, and x of L can be unique for all those values. So what we actually get is that x twiddle of n is the sum over all shifts of x of n shifted by big N samples. And so that's how we condense these, because x of e to the j omega has to reflect every value of x of n, right? It doesn't matter how many of them it's going to affect, it's going to change them. But x of twiddle can only have big N individual values. This is how all these extra values of x of n land up in x twiddle of n. They sort of get shifted down. And so this is like time aliasing, that we sort of fold it down onto itself and all the points line up. So here's a concrete example. If we start off with an 8-point sequence like this, and then we try and form its 4-point DFT, which means that we're trying to evaluate x of k for k equals 0 to 3, which means we're going to evaluate e to the j omega for, 4 divisions of the 2 pi sequence. So it's 0, pi on 2, pi, and 3 pi on 2. Right? Then we end up with a 4-point sequence, which is whatever it is. We can take its I DFT. We'll end up with a 4-point sequence in time, but what it's going to be is the sum of every 4-point shift of this thing. So we can take, here's the 4 points of the original sequence shifted by 0. Here it is shifted back by 1 chunk of 4. We could shift it back by more, but because it's a finite length sequence, that all the other shifts will be 0. But these things all line up. The first half and the second half, we line up. We get the values coming out like that, and that gives us our 4-point result. So graphically, we had, this is our original x of n with its 8 non-zero values. Here it is shifted by 1 block of 4 points, in this case shifted back, so we have the second set lining up. This is the, from this slide, the top one is the 8543, the bottom one, right, this is the 8543, and this is the 2221. And then we sum them up to get the overall result. Because x twiddle of n, it only exists over this range, right? It's only defined over 4 points. So there's no, we don't want to talk about what's happening outside of here. It's really just this finite length time axis that it's looking at. And so that's how we get this time aliased version. This property of the time axis sort of folding back on itself is, it's not how we normally think about time. We normally think about time as this thing that goes on and on forever. But when we're talking about this finite length, finite dimensional space, this is what happens. And actually, we can understand, in this case, the time as a loop, because it's in a periodic sequence. If you go past the end, it's like you come back to the beginning. And so the time axis has a circular behavior, which has a number of properties, which I'll talk about at the beginning of the next lecture. Any questions? All right, I'll see you on Wednesday.